Hello and good day to everyone. My name is Juan de Ruiz Jaramillo and I will talk about the poster stabilization of child-grade turquoise using sonochemistry. First of all, let's talk about the context of this project. Our team was contacted by Mr. Carlos Muñiz, owner of a mine in Baja California Norte, in Mexico, ACMTSA. The reason was to increase the hardness of his child-grade turquoise and thus increase its market value. And well, we accepted this project and we received a bunch of turquoise mineral, child-grade turquoise minerals. Before talking about gem-grade and child-grade, let's talk about the turquoise in general. As a manner of introduction, we have that the turquoise is an aluminum and copper phosphates. Its crypto-link structure is what gives its porosity, and in the region between northwestern Mexico and the southwestern of the United States, turquoise stands out as a mineral of importance. Now, what is the difference between child grade and gem grade? First of all, we need to understand that it goes by the same chemical formula and crystal structure. However, they have different density, hardness, toughness, and this leads to a different price. Talking about the price comparison according to Turquoise Quality Index, here we have how it does value the quality of a turquoise. First, we have the hardness that goes by 20 points, the type of improvement that goes by another 20 points, the composition, the cut, the availability, the color, the matrix, and size. This is so important because a great child-grade turquoise can only value up to $0.6 max, and a gem-grade turquoise can go up to $50 to $1,000. This is a huge difference. And now, currently, the turquoise is only used for ornamental purposes. For these accessories, the turquoise need to be gemstone grade. They cannot be child grade. The child grade does not have the necessary physical characteristics to be used in accessories. Here we have some brands that like Dior, Rolex, Philippe Nautilus, they need to use the turquoise but only gem grade. This is the whole purpose of a project. Go from child grade to gem grade turquoises. Now, talking about the background, there has been some general treatments like with wax, with plastics, or dyeing the turquoise itself. However, these methods are not permanent, and some of the wax and plastic are they have vulnerability to heat, so these kind of stabilization are not good for. They don't have the physical properties that we seek. However, we have the Zachary process developed in the late 80s. Not only improves the color and durability of turquoise, but also prevents oxidation and discoloration, making it the preferred method for stabilizing child-grade turquoises. We have general treatment to improve durability, surface treatment to enhance color, and general surface treatment to improve both color and durability simultaneously. In order to propose a turquoise stabilization process, we need to indirectly investigate what the Zachary process entails. The results indicate that the properties are very similar to those of natural turquoise, making it very difficult to distinguish them using general gemstone identification methods. In 2008, Quaneral analyzed the characteristics of a turquoise treated with the Zachary process and compared the results of those of untreated natural turquoise. And they and they concluded that it has a presence of silica, and the treated turquoise contains an unidentified resin. The only way to differentiate treated turquoise from pure turquoise is through X-ray fluorescence chemical analysis. With this data, we were able to propose a methodology for stabilizing turquoises. Before proceeding to the results, we have to clear that we are currently pioneers in gemstone stabilization. Now, the results presentation will be divided in three parts. The first part will be pre-stabilization results, the turquoise stabilization itself, and the post-stabilization results. In the pre-stabilization, we have XRD diffraction and X-ray fluorescence. And the post-stabilization results, we have Sharpie impact tests, beaker hardness, tribometry, and scanning electron microscopy. Talking about X-ray diffraction, four chalk-grade turquoises were selected individually and ground in an agate mortar, and a sample of the grinding of each one was taken for powder XRD analysis. These are the results of the four samples. Each grinding was analyzed using the powder XRD technique, and we compare each result with the American Mineralogist Crystal Structure Database records, searching for a triclinic structure. Comparing the results with the diffractogram from the database, it can be seen that the signals from the following planes coincide perfectly. The agreement between the experimental signals and those recorded in the database was remarkable, thus corroborating the presence of the triclinic crystalline structure characteristic of turquoise. The noise and the fluorescence of each diffractogram will be explained in the X-ray fluorescence section. The method was very similar to the X-ray diffraction. We ground for chalk-grade gems, and we took a sample of each one, and we went to analyze them in an X-ray fluorescence equipment. These are the results. The X-ray fluorescence results show a considerable concentration of iron in the turquoise samples. This is corroborated also by the results obtained through X-ray diffraction, where it denotes a fluorescence and an orange phase can also be observed in all the turquoise stones, which allowed us to safely affirm that iron is present in the form of oxides. The presence of silicon in the turquoise sample is explained by the very nature of the sample. As mentioned above, the samples come from mines, where it is very common to find silicates, which are compounds containing silicon and oxygen, and often also metals. We have to clarify that due to the presence of these different mineral compounds, the value of turquoise can decrease. This is because it is not a pure gem, which leads to a decrease in its value in the turquoise quality index, as I explain later. Even though the turquoise samples are not pure gems, then still can be subjected to the stabilization. Talking about the stabilization method, first we need to do silicon nanoparticles. We add 0.5 mole of TiO, 2 ethanol moles during stirring, and then while they are stirring, we add 5 water moles at 1 milliliter per minute, and then after that we adjust the pH at 3 with nitric acid, and we continue stirring at 60 degrees for 6 hours. And then we have our gel. However, we also have to dry the gel in order to obtain only the silicon nanoparticles. Talking about the stabilization, first we select our chalk-grade gemstones, and then we put them at medium vacuum during half an hour. Then these stones were then immersed in a solution composed of 8 parts of crystal PP resin and 2 parts of metacrylates, while maintaining constant stirring. Before adding the catalyst, 0.1% weight of silica was added, stirred again, and then the K2000 catalyst was added at a rate of 1 drop per minute, up to a maximum of 20 drops to ensure adequate mixing. 10 formulations were tested and discarded, among which was the opticon resin, which shows little penetration into the turquoise. Then, after having the turquoise sample immersed in the solution, were again exposed to a medium vacuum, prolonged for 60 minutes to extract gases. After this process, the turquoise samples were removed from the solution using a metal net and then placed back into the airtight container. A constant pressure of 40 psi was applied to the samples until the resin set, which can stain between 24 and 48 hours, depending on the thickness of the sample. Subsequently, and after reaching a certain degree of setting, an ultrasound treatment is implemented at a frequency of 120 Hz and 80 watts. This ultrasonic procedure causes a volumetric contraction in the resin, which translates into a generation of internal compression states that contribute significantly to improving the mechanical strength of the material. Now, every sample treated after this, every sample talk about now was treated by this stabilization method. We proceed to shape chalk-grade turquoise samples into rectangular prism with a specific dimension of 10 for 10, 10 times 10, 10 times 55 millimeters. And then we use the microhardness test as Swig-Rowell Indentech, and these are the results. Discussion of the microhardness test. The average indicates an improvement in the hardness of a stabilized turquoise compared to chalk-grade turquoise. The chalk-grade turquoise has some 0 in the microhardness test, so this has been an improvement in the hardness, of course. However, the average vary, and the standard deviations are in some cases much higher than what will be expected from the samples. In these cases, it is feasible to calculate an average of average to assign an expected hardness value to each stabilized turquoise in the future. According to our calculation, this value is 71.13 Beaker hardness with a standard deviation of 29.51. This value will serve as a useful reference for future studies and industrial applications of stabilized turquoise. Then these same rectangular prism, we use them in the Sharpie impact test, and these are the results for a total of 20 samples. These are the results, and the highest frequency was about 24 and 26 joules. The analysis conducted using the Sharpie methodology have revealed remarkable toughness in the materials examined. This finding suggests strong cohesion between the inherent porous structure of the turquoise, that is the matrix, and the dispersed one, that is the polymeric, that constitutes the composite. Although the current use of the material is not intended for structural applications, there is significant potential for its employment in future structural implementations. Talking about the SEM, 3 turquoises were stabilized with dimension not exceeding 10 times 10 times 10 millimeters, followed by analysis using scanning electron microscopy. 2 phases can be seen in this image. On the left side is the mineral phase, and then on the right side is the turquoise mineral resin composite. This image was taken in a fracture intentionally made to observe a composite from the inside. The surface resin can be seen unpolished, leaving a burr on the composite. The morphology of turquoise is observed in the form of slabs or sheets. As indicated by the cryptocrystallinity of turquoise, the sheets are rearranged randomly and parallel to each other. This explanation, when taken to a microscopic levels, is what is observed in these images. The morphology of turquoise is presented in the form of slabs. However, different spheres were found within the turquoise samples. It is speculated that they belong to an elemental metal. An EDX analysis is required to corroborate the nature of these spheres. Talking about the trigonometry pin on disk, a representative sample of chalk gray turquoise was selected and precisely molded to take the shape of a cylinder with a diameter of 1 centimeter. This cylinder was then sectioned longitudinally into 2 centimeters high pieces, which were subjected to the stabilization process. The trigonometry was taken on the Anton Part URB. This is an image of the before and after the test of this trigonometry test. The material ball, that is in this case stainless steel, is passed over the turquoise cylinder. And these are the results. All the samples are washed with alcohol before performing the wear test. One, we have, as you can see, the friction coefficient is very low for all the samples. There is two explanations for this. One is that we have a material with high wear resistance, or two, a Hertzian effect occurred during the tests. That is, when friction occurs, it generates heats. These heats inflicts in the resin and make it act as a lubricant that prevents wear. More rigorous tests are needed to corroborate wear. Finally, the conclusions are: the XRD analysis performed on the samples of chalk gray turquoise prior to stabilization allowed the identification of only tetraclinic structure, typical of turquoise. The XRF analysis confirmed the presence of iron and silica in the samples of chalk gray turquoise. The iron found in the samples is in the form of oxides, which explains the noise and the fluorescence in the XRD analysis. The use of sound waves during the stabilization of turquoise accelerates the polymerization reaction of the resin mixture, thus reducing the setting time from 48 hours to only 3 minutes. The results of the Sharpie impact analysis of turquoise indicate some remarkable toughness of the composite. The average of the result obtained is equivalent to 25.3 joules. The microhardness of the analyzed composites shows an improvement compared to the chalk gray turquoises, obtaining an average value of 71.13 microhardness and 29.51 standard deviation. The trigonometry result demonstrates low wear by stabilized turquoise. The coefficient of friction range between minus 0.137 and 0.4082. The analysis performed through SEM demonstrated the morphology of the turquoise in the formos of slabs. Spherical morphologies were also observed completely foreign to turquoise. And these are my references. And that will be all for today's video. Please feel free to reach if you have any doubt. Until then, goodbye.